Okay, so I just want to spend today just looking at a few binomial questions from the mixed exercise. We've pretty much covered all of the sort of the content, so I think it's just worth reflecting on what we have learned. So we're talking about binomial probability distributions, which are these situations which can be modelled as a binomial, and they have the four conditions that we talked about a week ago. So I like this question. We've got a completely unprepared student given a true or false test. Start off, if you can, by deciding the number of questions he gets correct. If it is a binomial, what are the parameters? What are the values of n and p? And then see if you can answer these two questions. Pause the video at this point, have a go for yourself. Okay, so hopefully you were able to say, right, it's a binomial where n is 10 questions, and if you're guessing, you've got a 50-50 chance of getting it right, so a half or 0.5. So I entered those on my calculator, and I made the lower and upper both 10 to work out the probability of just getting 10. You get a tiny, tiny probability, which if we go with 4 decimal places should be that. And then the probability that x is that he passes, so he needs to get 8 or more. I'll come back to my old-fashioned way of doing it here. So, he could get 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 8 or more is that. So I had 8 as my lower, 10 as my upper, and to 4 decimal places. That's the probability I got. Okay, a second question on the same page, page 96. Back a question actually, question 10. This is an example of a backwards one, an inverse one, but it's different to the ones we did the other day. I think this is really, really tricky. So firstly, you've got to state the conditions for a binomial. Those are the 4 conditions. That's a nice, easy 2 marks, hopefully. But then we're not told to start with what n is. We're not told how many doors this person is knocking on. In part B we are. So for part B only, we're dealing with a binomial where he knocks on 10 doors and the probability of success is 0.05. And we want to know the probability that he will have at least 2 successes. So with 10 doors, he could be successful at none of them, or 10 of them at least 2 is that, isn't it? So we want to know the probability that x is greater than or equal to 2. We can easily do that on our calculator. I'll get you to do that in a minute. But in part C, we're not told how many doors he knocks on. In fact, we are asked to work out the number of doors he knocks on. We want to know how many doors he would knock on so that the probability of getting at least 1 success is 0.99. So I'm going to draw my sort of curve. Remember, the binomial probabilities are not symmetrical. I just do that because it's a nice easy shape. I posted a little question, didn't I, in the last video? What do you need to happen to make them symmetrical? Hopefully you worked out the probability of a half. If you have a probability of a half, you do get a symmetrical distribution. Anyway, in this case, we don't know how many doors he's knocking on. We don't know that value there. We don't know this value here. But we want the probability of at least 1, so that's 1 or more, all of those probabilities, we want those to add up to more than 0.99. So this is another trial and error question, and I'm going to pause at that point and get you to have a little experiment with your calculator to see if you can work out the value of n. Okay, so for this one, I've entered my values, and probability of greater than or equal to 2 is 2 to 10, so that's at 4 decimal places. Okay, so for the second one, I don't know what n is. I want to know the probability of 1 or more, but I don't know how many I've got, but I need that probability to be bigger than 0.99. So okay, let's set my lower to 1. And let's try 10 to start with. Let's say that he knocks on 10 doors. Well, that's nowhere near 0.99, so having 10 doors isn't going to be good enough. Okay, so let's try 100, and let's work out the probability of 1 to 100. So what if that is 100? Ah, right, that is bigger than 0.99, but is that the smallest number that's bigger than 0.99? So let's try a smaller value of n. Let's go down to 80. So let's work out the probability of 1 to 80 if he knocks on 80 doors. Right, we've dropped below 0.99 again. So we know that this value here has got to be bigger than 80. It might be 100, it might be smaller than 100. Let's try 90. So then work out the probability of 1 to 90. Right, bigger than 0.99, so that could be 90. We want the smallest possible value though, so let's go down. Okay, I'm going to go down to 89 this time. So if I have 89 doors and work out the probability of 1 to 89, that's dropped below 0.99. So if I want this probability to be greater than 0.99, I need to have 90 as my n. And that means that he needs to knock on 90 houses in order for that to happen. 89 houses wouldn't be enough, 90 would be. That's a really tricky question. Okay, two more questions, both on page 96 that I think are worth you trying. I'm not going to go through them. I'm sort of hoping that you'll be able to do that. The last question I want to go through is question 15, which is actually the first one on page 97. It's the last one in the exercise, and it's the only example in the book of a problem I refer to as a binomial within another binomial. These tend to be quite popular exam questions. So let's delve into this one and see if we can make some progress with it. So what we're going to do is we're going to ignore parts B and C to start with. So I'm going to cover them up. There we go. We're just going to look at part A. Part A, she shoots 20 arrows. The probability of success is 0.6, and we want to know, I should cover that up as well, we want to know the probability that she hits the bullseye with at least half of her arrows. So for part A, we are dealing with a binomial distribution with n as 20, probability of success 0.6, and we want to know the probability that x is greater than or equal to 10. Okay, at least 50% means 10 or more, includes 10. So I'm going to do that on my calculator. I've still got the values from last time. So I've got 20 is my number of trials, 0.6 is my probability of success. I'm going from 10 to 20, and that's 0.8725. Good stuff, good stuff. Right, so now we want to look at the next part. Now she's doing something 12 times. The thing she's doing 12 times is this. And what we want to ask with each of those 12 sets of arrows is, does she hit the bullseye with 50% of them? So what we've got in part B and to start with is we've got another binomial. She's doing something 12 times, and the probability of success in this case is that she hits the bullseye with at least 50% of our arrows. Well, we worked out that probability in the previous question. So that probability there feeds into. Now you might be saying, hang on, this is bad maths. This is a rounded value. We shouldn't really be using rounded values. And you're right. But we have a problem because even the calculated value displayed here, that's a rounded value as well. So it's a problem that we're okay with. You know, we're being pretty accurate by going to 4 decimal places, so we'll work with it. So in part B, the probability that she hits the bullseye with at least 50% of her arrows in 7 of the 12 sets. So that is the probability that x equals 7. It's not at least 7, it's exactly 7. And so we need to enter these values on our calculator and work out that answer. I'll pause and let you do that. Okay, so I've got that. If you're using the textbook, it's so frustrating with the textbook that it sometimes does 3 sig figs. I think this one it rounded to 5 decimal places, but yeah, let's just stick to 4 decimal places. The reason we do that is because the old-fashioned tables that we had to use before we had the calculators are always done in 4 decimal places. Mark schemes are always done in 4 decimal places. Right, so the part C, same setup, still 12 sets of 20 arrows, still 50% hits the bull being the sort of success criteria, so we're still dealing with this. Less than 6, so I've drawn my picture. These are all the possible values, aren't they? 0 down to 12. So less than 6 is 0 to 5. So I've entered that on my calculator. So that's my parameters 0 to 5 and a tiny, tiny number. I move it over here. It is 0.0002474, so which is to 4 decimal places is 0002. I think in that question I would probably write both. So I'd write the long answer and then round it to 4 decimal places, and that way you're covering your bases. Okay, that's binomial done. So you've got a couple of questions, question 13 and 14, just to try to finish those off. And then we're going to move on in the next video. We're going to go back to me and Mr. Godber playing table tennis. And we're going to say what happens if what we expect to happen based on the probability doesn't happen. I can't wait. Hope you're all well. Take care. Hello, me again. Sorry. When you do 13 and 14, it'd be really nice just to get a quick picture of your attempts at those. I know you can see the answers in the textbook, but it's just, again, about reassuring us that you're engaged and keeping up. So if you are able to do that and email me, that'd be fantastic.